Hello and welcome everyone. I'd like to show today how we use Elixir in Anoma. To keep it very brief, Anoma is a distributed operating system that I work on. You can find more information on our website, anoma.net, where you can find blog posts, talks, and our forums, which have quite a good discussions. But I want to talk today about why Elixir is good for building a distributed operating system and what kind of gives it the edge over other choices that we may have picked. And I believe there's two main reasons as to why Elixir is a good choice for building a distributed operating system. The first being is that Elixir is fully interactable, meaning that Elixir is a live system. I can recompile the code live, and I can play with the values. Other languages do this better, such as, for example, Common Lisp, such as Smalltalk, and such as Factor. So, Elixir does not have the best interactivity. It has quite a lot, and I can show you some of it that it does have. For example, I can add numbers. I can inspect the result of adding numbers. I can even look at our documentation from within it, and I can even recompile code, which I didn't change any code. But to really show you sort of the benefits and how far you can push interactivity in Elixir, I wanted to talk about the second point, which does give it an advantage over those other languages. And that is namely the distributed programming model. To keep it brief, the Elixir programming model is one of actors. An actor is something that can receive and send messages, right? So I can send something like I can send myself, hello, Joe. And when I flush, I can see that I have the message in my mailbox, hello, Joe. A really useful abstraction on top of this is gen servers, which kind of give a way of giving a server an RPC, a remote procedure call API that lets you do calls and casts, meaning that you can do an asynchronous call where you send a message to the server expecting a response, or a cast where you send a command at the server not expecting anything. To more intuitively explain it to you, I will first show it to you live. So let us start our gen server. We're technically not really using gen servers, we're using an abstraction over it. So we have to we have our own public ID system. So great, we regenerate some IDs, and then I'm going to start our storage. So I just say start engine with the router, given the storage and some storage. Now it's very easy to send it messages. Like for example, if I were to send it the get, so let's say we do storage.get, storage, note that I can autocomplete the arguments. It looks like it accepts the key. It's absent because it's not there, but if I change it to put, it expects the key, then a value. So let's say it's now 1. And now when I get it, I get back a result, okay, 1, which is kind of nice. To show you what I mean by the system being live is that here's the code here. And the code that kind of handles this, so this is like the server code. So this is the public RPC API. It just is a bunch of things to router.calls and casts, which I could have done by hand. And then here's the gen server behavior. To show you something cool, we can make our own handle cast, and we're going to say hello. So I say this, and then I can say no reply, and I will just hand it back to storage, but I will do hello, Joe. So now if I were to recompile the code, which as you can see it's now recompiled, we get something interesting. So now we don't have that, so I have to do router, let's look at how we do it, router.cast, storage, and I believe I called it hello, say hello. So if I were to do this, we get back a message, hello, Joe. Note that this was the same storage that we just looked at. And in fact, we have better ways of visualizing how the system works. Erlang, out of the box, comes with some very interesting tools, such as Observer. So if I were to start up Observer, we can see our application here. So this is what our Anoma node looks like currently. We have some supervisor, which looks over nodes, meaning that if this node dies, it can be respawned. It'll have a new PID, but it can still be reserved. It can still reserve the same name. So here's the storage module, not the exact same one, but another one. And great, you can see what state it is. You can see its stack trace. So if it's processing any messages, You can actually look at its state, and it's quite nice for debugging. We can do this with what's in our storage tables too. So we can look at the table viewer, and if we remembered what our storage was, which was foo qualified and foo order, we can see them here in the monitor. As we can see here, so in the qualified table, we have the key 14230 being 1, because the cool thing is because we have persistent storage, we actually have a way of having storage being consistent across calls when real transactions come in. So for example, if I were to then put 3, we can see now that, oh, the latest one is 3, but we could still get the one at 1, which comes in quite relevant, which is very nice. So we get some really nice tooling just out of the box, along with checking things like how good is our load balancer, how good is the load chart. But another really nice tool in Elixir that I would like to show you all is sort of visualizing the system that we have. So over here, I have a tool called Livebook. This is made by the Elixir team. You can connect to your Anoma node by doing that. So I'm just going to say, here's my cookie name. I am now connected. So now when I evaluate this, we get to see the same chart. Note that this is some piece of code that helps us visualize what our software looks like. If I were to name the other node, I would be able to generate the same chart for this. Secondly, we get to see some cool things, like if you evaluate some code, you get to see slightly new actors on it. And then you get to see traces too. So for example, if you're curious, let's look at a simpler example than this. We can zoom this in to make more sense in a second. But what's very neat is that this is any piece of code and this is all running live. So if I were to do something more interesting, like, I don't know, this one looks like a very simple one where we are saying I'm adding some information to the logger and I'm looking at all the processes being measured. Let's see what happens. We can see that it's not very interesting. We just send a message to the logger and that's all. But if we do something more interesting, like sending to the mempool, increment some value in storage, we can see if we zoom in that, hey, who does the mempool message? Well, okay, if we look at the mempool here, let's see, we call transaction on it. This thing adds some things to the logger. It tells the executor to run some piece of code, and it tells the router, hey, here's some result. Further, we add some more logging messages, and then we give the result back to the user, which is very nice. You can do these kinds of things because the system is live, and the Erlang process itself, is a live system that you can mess with, recompile, and play with, right? Something amazing as well is that processes are cheap, right? So for example, we believe in interactive systems, and another great way that we leverage this and support further tooling is through a mechanism called examples. So what I want to show you is our enode file. So instead of having to remember arcane rooms, I usually just come, if I want to figure out how the node works, I can come here to storage and node and figure out, hey, I want to spawn this kind of thing, right? A lot of people do freshful storage, and if you find references to it, other examples use it. So let's use some of theirs. Let us use the intents. Yeah, eintent, sure. I can just call eintent examples dot node eintent dot a node, and let's say I want the return type is node. So now I just spawned an entirely new Anoma node. Right, it's that simple. It was very quick too. Watch, I can even show you. If we time it, which you can, you have really nice tools in this language to do such things. We can see that this took 90,000, I believe, milliseconds. And it's spawning all these different actors with an entirely new network configuration. What's great is that we can leverage this to making composable software. So for example, I have a thing called examples. This was directly inspired by the work at Glamorous Toolkit, which is a small talk system that I use in my own spare time. But what's really neat is that, well, you can reuse some things. So for example, if you want a basic storage, instead of running those commands that I showed you before, well, I could have just spawned storage like this. And now I have a node with storage. And the cool thing is that if we go to this code, it asserts things about how the storage ought to be. So every time I'm running something, and if, let's say, the storage broke, we would know the spot of isolation where it's broken. Unlike normal unit tests, where if the test breaks, it goes, you have to like look at like, say, 10 different unit tests. Some of them probably have repeat logic, and it's hard to determine and decipher where the failure point is. Examples kind of give you a way of, well, you can see the specific test which is failing, which let's say is empty storage, so you don't have to worry about, say, solved trades being bad, right? But we can look through this code and figure out what is the API of intents. And we can see here that we have some pretty interesting things, right? Where we make a node, and hell, let's call it, right? So if we do, this one is called eintent. Nope, I have to call it by hand. Let's see, and I were to do solve trade. I now have this, and now I can use the same tooling that we saw over here on it. Because, again, this is just, checking messages between things. So, if you had the processes here and you had visualization tooling, you could just use it. What's interesting is that I could even use this tool up here. So if I go there and I get storage, let me rerun it, and I want to get its server, let's see, process.where is. We can learn its PID is 13,238. And if you look at the processes, you can look at the processes here. It has to reload. Right, 1328, 13238, right here. We can see, here's the storage, right? We can even see the values. Like, oh, let's see, the ordering is solved trades, right? That's wonderful. Well, what does its table look like? Let's see. So we can look over here, we can look at it, right? The database is still great. Look, and we can see here that we have a bunch of messages here. A lot of this is logging messages. We have good logging mechanisms. So you can look at things like, oh, what kind of messages were sent, what kind of state, what kind of data is needed to really get to the state that you care about. So, there we can visualize the software quite nicely, which is very nice. Further, you kind of get to see some interesting things, and you can just get to play with it. Like, oh, what is this A for a Y? If I'm curious of just saying it, oh, here it is. There is some, let's see, there's some preference function, there's some deltas, there's some proofs, proofs of some transaction, there's some code here for the logic, and there's nullifiers and commitments. This is wonderful. Let's see how we implemented it. And if we look at this, oh, A for X is a transaction. Oh, and it's composed of more examples, which all sort of assert things. These ones I don't, because they're a bit, they're just kind of example data, but I do have examples of it. So you can understand the invariance of the data. This is not something that you really get readily with, say, a typed language necessarily, because proving things about dynamic properties is sometimes a bit difficult. So you can dynamically assert, here are properties in which we hold and how the API works. And what this means is that we have a fairly decently tested code base. So for example, if we run the tests, we can see that it takes 3 seconds, and if I ran it with cover like I did here, we can see that our coverage rate is 77.58%. With some of these not being really too relevant anyways, so it's most likely higher. But you get a lot of this. So the code base is fully interactive, and you can kind of visualize the data and see kind of what the data brings you. In the future, we plan on building more visualization software on top of Livebook that will let us visualize data types. Livebook is very nice in that it can give you things like diagrams. So if we were to make a diagram chart here, and we can evaluate this, we can see this inlined here. So in the future, we will be adding future code there. Further, what is really nice about Elixir is that, well, since it is a distributed language, it's very easy to talk to other servers. If I were to launch this code in prod mode, so if I were to launch this with prod instead of IEX, I can send messages to the server via our client. It opens up a Unix sock, as you can see here. And so if I do mix client, and I will ask it for help, let's see. We can submit some transactions, we can take a snapshot, and we can delete the dump. Or we can shut down the code. So let's shut down the server. We can see we can get warnings because it's going to shut down the server. So, there's a lot of logging information, and even if you don't like it, you can always change it. For example, I'm going to set the logger to all. So we're going to get all messages, and now if I were to rerun the same solver, so we can see that, wow, suddenly there's a lot of information. So we can see, kind of get a trace of what's wrong, meaning when things go wrong, and things do go wrong, you have the tools in your toolbox to help solve things. Thank you all for watching this. I hope, hopefully you can read the Elixir code that we have written, and I hope you found this bit interesting and kind of understand sort of the pros and cons of using, say, Elixir as a programming language for a distributed operating system.